We had some homework last night, worksheet number 13. Let's take a look at the answers for worksheet number 13 up on the board here, and let me know which of the 5 questions you need to go over here. Any of them? Jesse? 3? 3 and 4 we got? Going once, going twice. Okay, 3 and 4 it is. 3 says the initial acceleration. Kevin, you got another one? 5? Three says calculate the initial acceleration of a 50-gram, 20-centimeter long wire that carries a current of 0.6 amps if it's exposed to a magnetic field of 0.5 Tesla. First thing we got to recognize is we don't want grams, we don't want centimeters, we want kilograms, we want meters. The second thing we got to recognize is that since we're looking for acceleration, we're going to use F over m. Right? We always do that. When we're looking for acceleration in physics 30, let's say F is equal to m times a, get F. Get F somehow, and then plug it into the expression F is equal to m times a. Well, the force comes from the magnetic force. F is equal to ILB. We get the value of I and L and B. Let's plug them in here. I is 0.6 amps. L tells me is 20 centimeters. That's going to be 0.2 meters. And the magnetic field strength is 0.5 Tesla. We multiply those numbers together, and we're going to get what is that? 0.06? 0.06 newtons. We're going to take that value of 0.06 newtons and divide it by the mass of 0.050 kilograms, and we end up getting 1.2 meters per second squared. Remember, convert it to kilograms, convert it to meters, and whenever you're asked to find acceleration, let's use F is equal to m times a. 4. 15 centimeter long length of wire. Again, it's 15 centimeters. We've got to make sure that we're in meters here. 0.200 amps, magnetic field of 0.3 Tesla. If the wire is suspended, what must its mass be? What's the key word here in question number 4? The key word is suspended. If it's suspended, we're going to set Fg equal to some other force. And of course, that other force in this case is going to be the magnetic force. Mg is equal to ILB. We're looking for mass here, so it's going to be I times L times B over M. We got I, it's 0.200 amps. We got L, it's 0.15 meters. We've got B is 0.3 Tesla. We divide that by the mass, by the acceleration due to gravity, 9.81, and we should get 9.17 times 10 to the minus 4 kilograms. Okay, again, that big thing in this one is recognize that where it's suspended means Fg equals Fm, and recognize that we got to convert that length from 15 centimeters to 0.15 meters. Finally, question number 5. Calculate the mass of a 20 centimeter long suspended wire. Again, key word here is suspended. Fg equals Fm, but we got to recognize that that 20 centimeter length has to be converted to meters as well. So we're going to say m times g again equals ILB. We're solving for mass. Again, ILB over G. We got I, we got L, we've got B. Just make sure you convert L to 0.2 meters from 20 centimeters. Divided by 9.81, we should get 6.12 times 10 to the minus 4 kilograms. All right? We good there? All right, I want to take a quick look at the diagram you see up on the board. You don't need to copy this out. This is, again, just an application that may or may not ever appear on a test. It's not a curriculum objective. It's just one of those things that we use to describe principles that we've done, okay, put into practice. Over the last couple of days, we've talked about wires that carry an electric current in an external magnetic field. They experience a force. Okay, this is just a couple of wires, well, just one wire actually, that loops around through a magnetic field that will hopefully experience a magnetic force. Let's take a closer look at it. Here you've got an electric circuit down here with a battery has a negative end and a positive end. The electric current is going to go away from the negative end and it's going to go back toward the positive end. But there's a lot of stuff in between the negative end and the positive end of this battery. First of all, there's this black square there that's called a brush. That brush is attached to the wire, and it's touching this D-shaped thing that we call a commutator, but it's not actually connected to the commutator. It's kind of like my hand and the wall right now. They're touching, but they're not connected. Okay, if my hand and the wall are both conductors, then we can conduct electricity from my hand to the wall, but I can also move my hand around. This brush is not connected to the commutator, but it's touching the commutator. So it will allow electrons to flow through the brush to the commutator. The commutator is free to move. Okay, it's like my hand on the wall. It's free to move around. It's attached to the armature, this loop of wire that goes around like this. So if the armature moves, then the commutator will move with it. What happens the way that it's set up right now? You get electrons leaving the negative end of the battery. They go around this circuit clockwise. They go through the brush. They go into the commutator as it is right now. They go from the commutator into the armature, and they go around here clockwise, back to the brush, back to the commutator, back to the commutator, back to the brush, and then back around to the battery. So far, so good? Nothing's happened yet, right? Just an electric circuit that's a complete circuit because there's no gap for it. There's a path for electrons to flow all the way. Let's take a look at this wire. We'll call it wire number 1. Really, wire number 1 and wire number 2 are the same wire, right? It's just two different parts of it. So maybe we should call it part 1 and part 2. Side 1 and side 2. Side 1 experiences a magnetic force. Thumb in the direction of the particles, fingers in the direction of the field from north to south. The palm points, it's kind of weird here with the way they have this 3D diagram drawn, but you can see that this is supposed to experience a force upwards. So this wire experiences a force upwards. This wire over here, the one that's really the same wire, but the other part of it, is going to experience a force downwards. Thumb in the direction of the particles, fingers field, palm points downwards. What happens when one side of the wire, take a look at the paper that I'm holding right now. What happens when one side of the wire experiences a force upwards and the other side experiences a force downwards? It turns, it rotates. We get what's called a torque. Torques cause rotation. Okay, whenever there's a force off center, off the center of rotation of something, then something will rotate. Here we have two forces, one on one side of this armature, one on the other side of this armature. The armature ends up spinning 90 degrees, a quarter of a revolution. Now, when it goes a quarter of a revolution, this gap that's in the middle of this commutator, which is, we call it a split ring commutator because the commutator is split with this insulating gap, the insulator is now in contact with the brush, so no current forms or no current flows. It turns 90 degrees, the current stops, there is no longer any magnetic force. But because it's moving, it keeps spinning a little bit, just a little bit. It keeps moving a little bit past that point where the brush is in contact with the gap. So when it spins just a little bit past that, now we have what was wire 2 over here where wire 1 was. And now wire 1 is over here where wire 2 was. Now the electric current is still going to go through the circuit clockwise, but now it's going to go through wire 2 clockwise like this, and wire 1 clockwise like this. The current ends up being reversed. Although it doesn't look like it, it's still going clockwise. If you look at the paper again, it was going, let's number this here. Position 1, position 2, position 3, position 4. It was going, as you see on this paper here, through position 1 to 2 to 3 to 4. As it rotated 90 degrees, okay, it stopped, and then it made a 180 degree, okay, all the way around to 180 degrees. Now it's going clockwise still, but it's going from 4 to 3 to 2 to 1. You see that? So the current is reversed through the wire, but it's still going clockwise. Goes 90 degrees, okay, 90 degrees again. What happens? Current stops, but it keeps going a little bit. Goes 90 degrees again, we're back to where we started. Current's going clockwise again, 1, 2, 3, 4. The net effect of that is this. When it's going 1, 2, 3, 4, okay, with the first wire, wire 1, 2 is going to be pushed upwards, the other wire is going to be pushed downwards. When it goes around, okay, the wire that was pushed downwards is now pushed upwards. The wire that was pushed upwards is now pushed downwards, and so on. So that the net effect is that it keeps rotating around like this. That's an electric motor. Attached to the end of that electric motor might be a drill bit. It might be a mixmaster blade if you're trying to bake cookies. It might be the blades of a fan. Okay, it might be the wheel on a toy car. Whatever spins around, whatever turns because you put a battery in it, turns because of this. Because a wire that carries a current in an external magnetic field will experience a force. Does that make sense? The odds of you ever having to explain an electric motor, I think, would be quite small. The odds of you having to do something with electric force, or magnetic force, I should say, on a current-carrying conductor in some other application, okay, pretty good probably. All right, we're going to move forward here and talk about something called the generator effect. The generator effect is the opposite of the motor effect. Oersted taught us in 1819 that an electric current will generate a magnetic field. Two guys, Michael Faraday and Joseph Henry, taught us in 1831, just 12 years later, the exact opposite of that. An electric current generates a magnetic field, while a magnetic field can generate an electric current. But there's conditions on that. An electric current always generates a magnetic field, always. And that magnetic field is going to be circular. And a magnetic field only generates an electric current if one of two things happen. Number one, you've got a conductor and you've got a magnetic field. One of them's got to move. So either the wire moves through the magnetic field or the magnetic field moves relative to the wire. One of them's got to move. Okay, if you've got a conductor and a magnetic field and one of them moves, you will generate a current in that wire. As an airplane flies from east to west across the country, the wingspan goes parallel to the Earth's magnetic field, right? No, sorry, it's moving perpendicular to the Earth's magnetic field, right? There will be a small potential difference induced between one side of the airplane wing and the other end of the airplane wing. It's going to be small because the airplane isn't going particularly fast and it's not going through a particularly strong magnetic field. The Earth's magnetic field up where the airplane is pretty weak. But there will be a small magnetic field generated, a small electric potential difference generated across those airplane wings. If you move a conductor through a magnetic field, you will generate an electric current. Similarly, if the airplane was stationary and the Earth started moving somehow, then you would still generate an electric current in those airplane wings. Now, the second way to do it, we don't talk about this one as much, but if you change the value of the magnetic field, okay, the magnetic field increases or decreases or increases, decreases, then you're going to induce an electric current because of that. So you've always got to have a wire and a magnetic field, and you've always got to do something. Either change the value of the magnetic field, the strength of it, or you've got to move the wire, or you've got to move the magnets. Doing one of those three things will cause an electric current to be generated in that wire. When we generate electricity, large-scale production of electricity that is, it's always done on this principle. There are smaller scale things like solar power that are based on other principles where you're not moving a wire, where you're not moving a magnet. You're just generating electricity some other way. But all large-scale electricity production is based on this. There's lots of ways that we generate electricity. Hydropower is huge in Ontario. Okay, they use a lot of hydroelectric dams in Ontario to generate electricity. Nuclear power is also big in Ontario. There's a nuclear power plant in New Brunswick as well. Alberta uses mostly coal. We generate about 80% of our power by burning coal. All three of those things, however, burning coal, falling water in the case of hydroelectric power, nuclear power, all use the same basic principle to generate power. All three of those things produce heat. You burn coal, it makes heat. You had a nuclear reaction, it makes heat. The third one, I guess, the hydro dam doesn't generate any heat. The first two all both produce heat. That boils water. When you boil water, it turns into steam. Steam rises. Steam rises and turns a turbine. A turbine is essentially a bunch of wires, a bunch of loops of wire that go through a magnetic field. When that wire moves relative to the magnetic field, that generates a current. So whether you're generating power by coal or by nuclear reactions, ultimately you're producing steam that rises, moves a wire through a magnetic field, produces electricity. In the case of hydropower, as they use a lot in Ontario, the water falls. As the water falls, it turns a turbine. As that turbine turns, a wire moves, or a bunch of wire moves through a magnetic field and generates an electric current. When I was a kid, I've got a light on a light for my bike now, but the light for my bike now is a bunch of LEDs on the front of it, and it's powered by batteries, and it lasts for a while because LEDs don't use very much power. When I was a kid, I had a light for my bike, but lights on bikes were almost non-existent when I was a kid. The light on my bike when I was a kid wasn't battery powered because the lights were so terrible back then that your battery would die in half an hour. It wouldn't be any use to you. The light on my bike when I was a kid was actually attached via a wire to a thing that was attached to the fork on my bike, to the front wheel of my bike. So this thing that was attached to the fork of my bike actually had this rough thing that rubbed against the tire, the front tire. And as I pedaled, the front tire turned, and as the tire turned, it turned this thing on this device that was attached to the fork of my bike. The light lit up. Okay? I generated power by pedaling, by turning the wheels of my pedals, and therefore the wheels of my bike. I generated electricity by, inside that little device, moving a wire through a magnetic field. Does that make sense? We'll talk a little bit more about that on Tuesday. We'll do a little demonstration with this on Tuesday, and then we'll be ready for our test on Thursday. Have a good weekend, everyone.